Thank you very much. So I would like to thank Simons Institute for inviting me to participate in this workshop and this special semester. And so there will be two tutorials on this subject, the GCT Chasm. So today is the first tutorial and tomorrow will be the second tutorial.
Ketan, can you speak louder or maybe the microphone can go up somehow?
Hello? Can you hear me?
They also can.
Can you hear me?
It's okay.
Yeah? Okay. So the title of this tutorial is the GCT Chasm, which refers to some fundamental difficulty at the interface of geometry and complexity theory, which the GCT program is trying to overcome. So the goal of this tutorial to explain what this difficulty is and what its implications are for complexity theory and algebraic geometry. So this is going to be the main reference for this tutorial as well as the second tutorial, Geometric Complexity Theory 5. This is the fifth paper in a series of papers on the geometric complexity theory programmed towards the permanent versus determinant problem. In short, we'll refer to as GCT 5 henceforth. So the abstract of this appeared in Fox 2012 and the full version may be found on the archive and also on my homepage. Okay, so let me begin with the lower bound, which was the beginning of the GCT as per my understanding of GCT in a broad sense to be made precise soon. So what this lower bound says is that the max flow problem, we don't have to know what the definition of this problem is, it's a fundamental combinatorial optimization problem in P, cannot be solved in the PRAM model without bit operations. So this is the usual model for parallel computation in complexity theory. The difference from the usual PRAM model and this is that in this model the bit operations are prohibited. So you are allowed to add, multiply, take comparisons and so forth, but no bit operations. So for example, in the max flow problem, the input is graph with the edges labeled with capacities. You can't take, for example, OR of capacities and so forth.
Is this the same as circuits, or is this I don't quite get what this PRAM model is.
Just the usual. I won't go into the definition. Just the usual model of model used in complexity theory.
Algebraic
You can
circuits.
do branching.
Yeah.
Okay, circuits with PRAM.
But bit operations are not allowed. And it says that the max flow problem cannot be solved in the PRAM model without bit operations in polylog of n time using polynomial number of n processes, where n denotes the total bit length of the input, not just the size of the graph, but also the total bit length of all the capacities. So this is not an algebraic lower bound, it is a Boolean lower bound. That is the important point. And since max flow problem is P complete, this is a formal implication of the fundamental uniform Boolean P not equal to NC conjecture in complexity theory. So this is the number 2 conjecture in complexity theory. The number 1 conjecture is P not equal to NP conjecture, because since max flow is P complete, obviously it can't be solved in the unrestricted PRAM model in polylog n time using polynomial number of n processes. And this says the same thing with the added restriction of bit operations. This PRAM model without bit operations is a very powerful model of computation. For example, the usual algebraic things which you can do fast in parallel, such as the determinant computation or efficient factorization of multivariate polynomials and so forth, can be done very efficiently in this model. And virtually all known fast parallel algorithms for algebraic problems or for weighted combinatorial optimization problems which work fast in parallel actually belong to this model. So this is a very powerful model of computation in which the determinant and things related to determinant can be computed efficiently. And this is currently, to our knowledge, the only known non-trivial implication of such a fundamental uniform Boolean conjecture. P naught, yeah?
The max flow problem here is not defined as a polynomial, right?
Yeah.
It's a Boolean problem.
Yeah.
Okay.
It's a Boolean problem. It's a Boolean problem. The capacities are given. So this is the only known non-trivial implication of the fundamental uniform Boolean P not equal to NC conjecture that can be proved unconditionally in a model of computation that is so powerful. So that is the first thing worth noting about this. The second thing worth noting about this result is that though this is a Boolean lower bound problem, the proof goes via algebraic geometry. A priori it is not clear why do you need algebraic geometry when actually the problem itself is completely about can be stated in the Boolean setting. And secondly, it goes via upper bound techniques. Again, it is not clear, that is, it actually constructs fast in parallel given any circuit in this model a counter example on which it fails. Now a priori it is not clear why do you need to do anything efficiently, find such counter examples efficiently when all you need to do is just prove existence of such a circuit by some non-constructive way. But the fact remains that this is the only way this proof was found, and there is no other proof for this result so far. Secondly, and this was actually, so this, the GCT in a broad sense is a geometric approach to the fundamental lower bound problems via upper bound problems in algebraic geometry and representation theory. So in some sense, this is called the flip. This is actually the guiding strategy of the GCT program. So in that sense, this may be regarded as the beginning of the main proof technique, the proof strategy of the GCT program. And the third thing to be noted about this result is that now it has been more than 2 decades and there has been no fundamental advance over this lower bound in such a powerful model of computation. So what do I mean by fundamental? So for example, you can ask, can you prove the similar lower bound for the computation of the permanent in this model? Now the proof technique of this lower bound breaks down because it uses some results in algebraic geometry due to Milnor and Thom degree based results which can't be used since permanent has small degree. And in fact, the GCT program for the permanent versus determinant problem was formulated after this result to basically emulate this proof technique in the setting of the permanent versus determinant problem. But that has turned out to be quite a task, and this program as it has not delivered any nonlinear lower bound for the permanent in this model, nor do we know any other technique which gives a nonlinear lower bound in this model so far. So the question that we are going to ask today is, why is improving on this lower bound, why has it turned out to be so difficult? Is there any fundamental obstacle which is blocking the progress because of which we have not been able to improve this lower bound? And the answer is yes. Actually, that fundamental obstacle is precisely the GCT chasm that I referred to, and it is because of that, as we will see, that improving on this lower bound has turned out to be so difficult. And if that chasm turns out to be as massive as it seems to be, then this lower bound result, which was the beginning of the GCT program, may remain the only such lower bound, that is the only non-trivial implication of such a fundamentally Boolean uniform conjecture of complexity theory in such a powerful model of computation for a long time to come, until that difficulty is overcome, if at all. The reason I am starting with this is quite often it is asked, has GCT program delivered any lower bound? So actually the answer is that yes, actually it began with a lower bound, and this is the only such lower bound known so far, and now it seems that it is going to be really hard to improve upon this lower bound because of the difficulty that I am going to talk about today. So now let us before I define that difficulty, let us state formally the same problem, the problem for permanent in this model. So as it turns out, so goal is we want to prove the same lower bound for the permanent. But for the permanent, as it turns out, even the algebraic version is very hard. That is, even if you don't worry about the bit lengths, just allow operations over complex numbers. That is hard enough already. And since the main thing is that we want the model of computation to be powerful, that is, at least determinant can be computed efficiently and things related to the determinant. Until the model of computation is so powerful, the real difficulty of the lower bound problem is simply not going to arise in that model. So let us just keep the determinant in the model, throw away everything else, and what we are led to is the well-known permanent versus determinant problem in complexity theory. And the fundamental conjecture here due to Valiant is that the permanent of an n by n variable matrix cannot be expressed as a symbolic determinant of size m, that is, as the determinant of an m by m matrix whose entries are possibly non-homogeneous linear functions of the entries of x if m is polynomial in n. Almost equivalently, this says that the complexity class Vp associated with the determinant, ignoring that subscript x which stands for skew, I'm not going to worry about that technical detail, is different from the non-uniform complexity class associated with the permanent. Now, this is a stronger version of this conjecture which was proposed in GCT I, the first paper in a series of papers to the GCT program. And the stronger version says that the permanent of an n by n variable matrix cannot even be approximated infinitesimally closely by symbolic determinants of polynomial in n size or even O2 to the n to the epsilon size for some small enough constant epsilon. And we say that permanent cannot be can be approximated infinitesimally closely by symbolic determinant of size m if for any delta, that is precision factor delta, we can come up with some symbolic determinant over the complex numbers depending upon that delta such that the coefficient vector of the polynomial computed by that symbolic determinant is the distance of that from the coefficient vector of the permanent is less than that delta. So that is, and the delta can go to 0. So that is what I mean by that. So the permanent of an n by n variable matrix cannot be approximated infinitesimally closely. Now, though this conjecture is stronger, it is not expected to be much harder than the original conjecture. The reason is that all the lower bounds that we know so far for the permanent, the lower bound for exact computation and the lower bound for infinitesimally close approximation go hand in hand together. So, for example, there is a well-known lower bound due to Mignon and Rassayre quadratic lower bound for the permanent. The same lower bound holds for infinitesimally close approximation. The basic idea is the same. Similarly, later on we will see in Kayal's talks that there are lower bounds for the permanent for many restricted models of computation. Essentially, the same lower bound holds for infinitesimally close approximation. And of course, we are not asking that the exponent of the lower bound be the same for both the things. We will allow polynomial scaling. So what we are saying is that, say for example, you prove a lower bound for exact computation, say n to the a, the same technique should be able to give a lower bound of the kind n to the a by 100. So any scaling of the exponent is fine. So up to so far even you don't even need scaling, but we allow such scaling. So as long as you allow such scaling, all the evidence so far suggests that the difficulty should be comparable. And now with that, this is the main result of this article. It says that this stronger form of GCT1 conjecture, where the lower bound is of the kind O of n to the 2 to the n to the epsilon for some small enough epsilon, this stronger GCT1 conjecture implies that a certain problem in algebraic geometry called NNL, which I am going to describe precisely later on in the talk, called the problem of de-randomizing Noether's normalization lemma for the orbit closure of the determinant. So what is the orbit closure of the determinant? It is simply the set of the orbit closure of the determinant of size m is basically just the set of all points that can be approximated infinitesimally closely by symbolic determinants of size m. So it turns out, it's a non-trivial fact from algebraic geometry that this set actually is a variety. So that is the orbit closure of the determinant. Now in algebraic geometry, there is a very foundational result called Noether's normalization lemma due to Hilbert, and the problem of de-randomizing that lemma, so it, in some sense measures how difficult the variety is. Okay, so it is actually the difficulty of the variety, and so that problem of de-randomizing Noether's normalization lemma for the orbit closure of the determinant can be brought down from X space. So where here X space is the Boolean complexity class, which means that it can be done in using workspace that is exponential in m, the lower bound parameter. Okay, so where it currently is to date, which is basically the class of problems which can be reduced to computation of the determinant. It is contained inside the complexity class P up to a quasi-prefix. I'm ignoring a quasi-prefix which can be removed by slide strengthening.
What is a quasi-prefix?
Meaning instead of polynomial signs, it could be 2 to the polylog n sign determinant, polylog m size. So, okay, so for the mathematicians who may not be familiar with the complexity classes, here is a snapshot. So here is the X space. Here is the complexity class det, which is the class of problem that can be reduced to determinant computation. Then the usual complexity class P, the class of problems that can be reduced to that can be solved in polynomial time. The P space, the class of problems that can be solved in polynomial space. X, the class of problems that can be solved in exponential time. X space, the class of problems that can be solved in exponential space. Now currently this problem NNL is here in X space, and what it says is that if the stronger form of the permanent versus determinant conjecture is true, it would essentially come here, ignoring quasi-factors, and so this is where it should be. So this gap between the existing complexity and what the complexity ought to be is what this formal gap is, what we shall refer to as the GCT chasm. So this is the basically definition of the GCT program. This is what it is trying to overcome. Now given the magnitude of the gap, it seems that the problem is going to be quite difficult. Of course, we don't know what that quite difficult is. But more than that, the important thing is if the gap is so huge, how can we be sure that actually we can go from X space to P? Because if the gap is so, I mean, there could be some fundamental reasons blocking us, given that the gap is so huge. And actually, today I am going to present some fundamental evidence from the field of complexity theory and also algebraic geometry and representation theory, which suggests that actually it may not be possible to bring the problem NNL from X space to P or even to sub X. That is the class of problems which can be solved in 2 to the m to the epsilon time, where epsilon is arbitrarily small. And so there is now a serious possibility that it may not be even possible to bring NNL from X space to P or even to the complexity class sub X. Now if that happens, then what? So that is what I mean. If the chasm cannot be crossed, then what happens? So suppose that NNL is not in sub X, which the fundamental evidence in both these fields that I am going to present suggest. Then what are its consequences? So this is a consequence of the main result in conjunction with the standard techniques of algebraic complexity theory. Say, assume that the generalized Riemann hypothesis hold over number fields. Assume that Valiant's conjecture is robust, that is, VNP not equal to VP implies that VNP is not contained in the VP closure, which is basically saying that if permanent cannot be computed exactly by polynomial size symbolic determinants, then permanent cannot also be approximated infinitesimally closely by polynomial size symbolic determinants. Basically it says that if you are just interested in polynomial lower bounds, the lower bounds for exact computation and infinitesimally close approximation go hand in hand together up to some scaling. So as I said, so far there is no scaling. The same lower bound n square which holds for exact computation holds for infinitesimally close app. But if you allow scaling, say the lower bound, so you prove a lower bound to n to the a for exact computation. Let us say the lower bound for n to the a by 100, where that 100 doesn't depend upon is predetermined thing, would hold for this. So all the evidence so far suggests that Valiant's conjecture is robust. So assuming GRH and robustness of Valiant's conjecture, then it says that NP is actually contained in P/poly. The polynomial hierarchy collapses to the second level, and then under some stronger assumptions which I won't go today because they are somewhat more technical and algebraic geometers and representation theories may not be familiar with that terminology, P is not equal to BPP. So if it turns out that actually this problem cannot be brought down from X space to P or sub X, as the current evidence suggests, then there would be actually a collapse at a foundational level in complexity theory, because these are actually the foundational conjectures of complexities.
Can you explain what is P/poly?
It's a non-uniform version of polynomials, just circuits. Okay? So there is a serious problem here. So that's why I'm not going to talk about what the GCT program is. I'm going to simply talk about what this difficulty is, and I'm just going to present before the field the facts, the results, and all the evidence from complexity theory itself and from algebraic geometry that now points against these foundational conjectures. And then it is up to the field of complexity theory to justify why this conjecture should hold despite all this evidence to the contrary. So now this is the outline of the talk. So the first, for that I'm going to reformulate the strengthened form of the permanent versus determinant conjecture in terms of the orbit closures. Then we will give a complexity theoretic and representation theoretic evidence for why the orbit closure of the determinant contains points that do not have small circuits. Now this is very counterintuitive, because if you take m by m determinant, take its any linear transformation, it has small circuit. Now what it says is that, but if you take its approximation going to the closure, actually there is an exponential blow up in the circuit size. So the boundary of the determinant is pathological. It contains these polynomials which actually the circuits, there is an explosion in circuit size there. This is going to cause all the problems, because once you know that there is an exponential blow up on the boundary, all kinds of things start going wrong. Then we will precisely define the problem NNL of de-randomizing Noether's normalization lemma for the orbit closure of the determinant. Then we will explain why its current complexity is so high, that is X space, and that is essentially because of this, that the orbit closure of the determinant contains points that do not have small circuits. Then we will explain why the strengthened form of the permanent versus determinant conjecture from GCT1 brings it down to quasi-date. Then we will explain why the evidence, all the complexity theoretic and algebraic geometric evidence, why it may not be possible to cross the chasm and bring this problem from X space to P or even sub X. And then of course that result that I just mentioned holds, and then we will see what its consequences are, say a few words about how to deal with the situation. So now we'll start one by one on all these things in precise way. So the first, reformulation of the problem in terms of the orbit closures.
He has a question.
I have a question. So the theorem where the NLL is not in sub X implies the other conjectures that they have believed of it implies this counterintuitive complexity results. How general varieties do you need in the NNL for?
Just orbit closure of the determinant.
The orbit closure.
That's it. That's it. And on this, all the evidence in algebraic geometry and representation theory, there is explosion there. That's it. So you don't worry about anything else, just the determinant. And in fact,
There are varieties for which you can do an analysis.
yeah. But determinant orbit closure is where all the problems occur. Okay, and that is why I said the lower bound problem doesn't begin in an arithmetic model in which you cannot compute determinant and things related to determinant. In most importantly, factoring polynomials. A multivariate polynomial. So now, I define the orbit closures. So let V CMY be the space of homogeneous polynomials of degree m in the entries of a variable m by m matrix with the action of G equal to GLM square C that maps any polynomial f of y in this space V to f of sigma inverse y for any sigma belonging to G, thinking of y as an m square vector. So this is the space of homogeneous polynomials of degree m in the entries of variable m by m matrix y with natural action of GLM square C. Let PV be the projective space associated with V, and let G equal to determinant y belong to projective space associated with V. So since this is a homogeneous polynomial, we can think of it as a point in the projective space V. And now you define the orbit closure of the determinant denoted delta det m as you take the orbit of G and take its closure in the projective space in the usual complex topology, or is the same thing as the closure in the Zariski topology. Now for the orbit closure of the permanent is defined similarly, but now we have to be a bit more careful. So let X be the lower right n by n submatrix of Y, and let Z be any element of Y outside X. Okay, and let f of Y be equal to Z to the m minus n times permanent of X. So we are just scaling it up, padding it up, so that this element now belongs to the projective space V. And now define the orbit closure of this padded permanent as delta permanent nm as you take the orbit G of F, take its closure, and in the projective space. So this way you get the orbit closure of the determinant, this way you get orbit closure of the permanent. So with that, now the stronger permanent versus determinant conjecture from GCT1 is now equivalent to that this orbit closure of the permanent is not contained in orbit closure of the determinant if m is polynomial in n, or more generally O of 2n to the epsilon for a small n of epsilon greater than 0. So in what follows, we are just going to use this. This is what is being used. Now, what is the main difference between original Valiant's conjecture and this conjecture? The original conjecture is about this constructible set, that is, you are actually taking just the linear transformations of the determinant with possibly singular matrices instead of GLM square C. Now, that set is very bad from the algebraic geometry point of view. It is called what is called a constructible set.
It's an affine variety, though. It's just not a sub-variety of that.
Yeah, but if you take the projection, I mean, it's, and then, whereas this conjecture is a statement about the variety which is its closure. So now the basic principle of algebraic variety says, geometry says that the difficulty of a constructible set is controlled by what lies on its border. Because though, like for example here, just take the simplest case, I mean this is affine variety, this is not very bad. Like though we want to understand this is not a part of the problem. To really understand that, you have to understand what goes on here. The singularities is actually what controls everything, though it is not a part of the problem. And that is what algebraic geometry is all about, trying to understand the varieties by what happens at pathological points. So these pathological points actually is what, they are the ones that govern the difficulty of the permanent versus determinant problem. And so the main thing about this conjecture is that that part, which is actually the difficulty of the problem, is just made part of the statement. So now, if the difficulty of a constructible set is controlled by what lies on the border, now we ask what lies on the border of this singular, the transformations of determinant y, and since G equal to GLM square is actually dense inside MM square C, we might as well just worry about the border of the orbit of the determinant, orbit of G, determinant under G. So now let us make this fundamental definition. A family of points Pm, where Pm belongs to the orbit closure of the determinant, is called a family of bad exterior points if Pm does not belong to Vp. That means that Pm cannot be computed by a small circuit over C. Okay, that is, so now intuitively you think that since the linear transformations of the orbit of the determinant, everything has small circuit size, hopefully everything on the orbit closure should also have small circuit size, but actually that is where the problem is. Now, if, for example, if assuming GCT1 conjecture, if such bad exterior points exist, then assuming the strengthened GCT1 conjecture, such a family has to be what is called VNP intermediate. That is, VNP intermediate polynomials are the ones that are neither VNP complete nor in P. Okay, so for example, in the case of NP versus P, you have this Landner's result which says that there are problems which are neither NP complete nor in P. Okay, so it is an analog of that here. Now, if such thing did not exist, then such bad exterior points could not exist, because if this bad exterior point existed here, then it would follow from this conjecture that actually, if such thing did not exist, which means that anything here either has small size, otherwise it has to be VNP complete. But if it is VNP complete, it would follow that permanent can be approximated infinitesimally closely by symbolic determinants, and that is precisely what the conjecture says is not true.
What do you mean by GCT1 conjecture now? What do you mean?
That the permanent cannot be approximated infinitesimally closely by symbolic determinants of size. Here, in this case, you could actually even take polynomial size. Okay, so unfortunately, VNP intermediate polynomials exist. Now, this is a result of Burgesser, which is an analog of Landner's result in this setting, which basically says that the dichotomy failed. This is referred to as failure of the dichotomy. They would have been dichotomy if everything were either VNP complete or in P or in VP, but there are things in between. Now, Burgesser's result is non-constructive, doesn't tell you what those things are. It just says there is something there. But that opens the floodgate, which means that now there is a possibility of such things. There are things in between, and now such things can happen, can enter into the orbit closure of the determinant. And the conjecture is that that is what happens. That determinant has bad exterior points. And now what we are going to give is the important evidence from complexity theory and also representation theory for why such bad exterior points should exist. And then we will give As I said, Burgess's result is very non-constructive, doesn't tell you how to construct such points, but then will give natural constructive candidates for representation theory, which actually had this kind of behavior. So these are the two next things that we want to do. So for that, we have to define this notion of what is called Newton degeneration. Okay, so given any symbolic matrix Z of size m equal to polynomial in n over the variables z1 to zn, let Newton of Z be the Newton polytope of determinant Z expanded as C alpha Z to the alpha, where these are the various monomials in Zi's. Then given any face f in this Newton polytope, not necessarily a facet, any dimension, let determinant fz be the truncation of this at that face. So you just restrict alphas to the exponents which lie in that face. Okay. So the Newton z is basically the convex cell of all the exponents that are occurring here in the determinant expansion, and you, given any phase, you just restrict yourself to the alphas which occur in that phase. So call it the Newton degeneration of determinant of z associated with the phase f. Now the fact is that determinant f of z belongs to the orbit closure of the determinant. This aim is the same as this f for any f and z as a whole. And this basically, to those people in Grobner basis theory, this is basically the initial form. With you just take a weight function which achieves optimum over that phase, then this is an initial form with respect to that. So there is a standard deformation argument in Grobner basis theory, and which would basically tell you that this would have to occur in the orbit closure of the determinant. Now the question now we ask next is, when can you expect this to have small circuit size? Now this by definition determinant of z has a small circuit size. But in general, when can you expect this z, determinant of fz, to have small circuit size for given z for any f like this? So let us start with a fundamental example which will give us an idea as to when you can expect the determinant fz.
Are these Newton degenerations in the Valiant world? Is this looks like just you're killing some things, so it's just
killing everything except the initial form. This is the initial form with respect to. So
is it in the image of the endomorphisms, or do you really?
No, of course not. Of course you need the closure.
Okay.
Of course you need the closure. Yeah.
Well, that was my question.
Yeah. It's a closure. Okay. So this is the initial form with respect. So yeah, you need the closure. Yeah. So now this is an important chaos result. What says that Newton degeneration of the Tutt polynomial. So you take any non-bipartite graph. With that you associate a skew symmetric variable matrix which has entries zij in the ijth place if there is an h from I to j and I is less than j, and 0 otherwise, and you make it skew symmetric. So the determinant of that is called the Tutt polynomial associated with that non-bipartite graph. It is the square of the so-called Pfaffian, and the Newton polytope of that Pfaffian is basically the perfect matching polytope for that non-bipartite graph, that is just the convex cell of all the perfect matchings. And this is called Edmonds perfect matching polytope because this is a fundamental work of Edmonds, who gave actually the facial description of that polytope. So it says that the Newton degeneration of the Tutt polynomial associated with the Edmonds perfect matching polytope for any non-bipartite graph has every Newton degeneration has a small circuit. So what says that you take the perfect matching polytope, you take its any phase, you degenerate this polynomial to that phase. Doesn't matter which phase you degenerate to, you will always get whatever you get always has a small circuit.
You switched out to Boolean search. This is a result about Boolean search.
No, over complex thing also. Okay, so what is this? So what I'm saying is,
Perfect match.
so you take Zij, okay, and 0 otherwise minus Zij, correct, like this, and then of course I mean this determinant is defined over rational. So when you actually you will use the description of Edmonds thing and you will use Strassen's thing. So I think the final thing would turn out to be over rationals. Okay, yeah. In this case, yes, everything would, you won't need complex numbers. That is what you are asking, correct? Yeah, you won't need complex numbers here. Now, of course, Edmonds perfect matching polytope is very special. I mean, this happens because Edmonds perfect matching polytope has exponentially many faces. And the amazing thing about this polytope is, and in fact this was the beginning of the theory of P, that even though it has exponentially many facets, the membership problem for this polytope is in P. And other thing is that if you take the determinant, the third polynomial, given any exponent, whether it occurs in this expansion is easy problem, because that just means whether alpha corresponds to a matching. So it has these two properties. This membership of a monomial in this expansion is easy, and this in the polytope, the Newton polytope, even though it has exponentially many faces, still has the membership problem in P. So as long as your polytope has this property, and this is a fundamental thing, I mean everybody knows that this is a kind of very exceptional behavior in complexity theory. As long as your Z, Newton Z, has this kind of properties, you can reasonably expect that actually you can restrict it to any phase and you will still get small circuits. But in general, this is not expected because of the complexity, these are complexity results. By Fournier and Mallard, we say that the problem of deciding if this is Z alpha, okay, Z alpha occurs in determinant Z, given Z and alpha as above, is hard, that is C equal to P hard, which means as hard as deciding if permanent is equal to some value specified in Boolean. So it's the decision version associated with permanent, so it's very hard. In contrast, for the perfect matching polytope, this was trivial. I mean, it was just in date. This problem was in date. So in general, this problem is hard. And also the membership problem for this is P hard, as to be expected. So in general, it could have exponentially many faces. And in general, you would expect that actually the time required to do the membership thing would be exponential. So now, if these two holds in general setting, then in general, what this means, I mean, there is a fundamental hardness versus randomness principle in complexity theory, which says that if these C alphas are hard functions, they kind of behave randomly, okay? I mean, you can expect that they are behaving randomly. And now this Newton polytope has exponentially many faces, so if you just choose any of the faces which has exponentially many vertices on it randomly and restrict it to that random thing, what you get, actually you have removed exponentially many things and you are actually restricted to a random phase. What remains, the pattern is all lost. It kind of looks random. So with high probability, you will expect that what happened for this perfect matching polytope won't happen. The conjecture would be that the complexity would shoot up. So this is actually the reason, and this is the main reason, this work of Edmonds and all these results, Kia, Fournier and this, which together indicate that actually in general, I mean, what happens for Edmonds perfect matching polytope is a very exceptional phenomenon. In general, such a thing is not going to happen, and the things would shoot up, and all of them actually occur in the orbit closure of the determinant. So this is where the problem begins. Now we want.
I don't understand. Why are you expecting it to shoot up from these three statements?
Because this says that these C alphas behave randomly. And determinant is a very special thing, and you are restricting that to the random phase. So in the determinant, I mean, almost all deformations, if you take the coefficients of determinant perturb them slightly, almost always you will have the high complexity. That is what the thing is.
It's a belief. It's a belief.
But I'm just...
No, it's a belief, but actually this is an upper bound problem. No, it's a belief, meaning the hardness versus randomness principle is a belief, of course, yeah.
Okay.
Even though it's a belief, what is the evidence or the motive? I kind of missed the train of reasoning.
Maybe can I make a comment? So this membership problem, if you take the Newton polytope for the polytope that you get when you look at perfect matchings,
Yeah.
and you ask for the complexity of the membership problem, then we believe it's better than P. Then what do we?
Then it is P.
Yeah, but below P, how?
No, below P I don't know. What about below P? Doesn't matter.
Detecting whether a graph has a perfect match.
Yeah, that can be done in very NC also. It's,
That's what you put. Yeah, I think.
yeah. So it doesn't matter. I mean, so the
That's not the point here.
I mean, it is not in P. That not in NC is not a matter. But the point is, in general, these things are actually hard to compute. Okay, so these are kind of random things.
You're saying they're hard to compute because you can't determine the coefficients?
Yes, this is hard. C equal to P complete.
But, okay.
They're complete, so they're hard to compute. So the hardness versus randomness principle suggests that they should kind of behave randomly, and you are restricting it to this. So that would kind of suggest that this should shoot up. And of course, this is a thing that can be falsified. This is going to be the conjecture. All you have to show is that the Edmonds kind of result holds for any symbolic determinant. That would be a phenomenal result, because that itself would kind of show that and we'll see that from representation theory that is not expected, because Edmonds polytope is a very special kind of thing. You don't expect the Edmonds kind of results like this kind of result for arbitrary Newton polytope, and we'll see from the representation theory also why that is not expected. So now we want to, so this is the complexity theoretic intuition, and now we want to formalize it. So formalizing it, given any family determinant of Zn in VPS, this A stands for skew, which corresponds to the determinant, the class of polynomials which can be computed by small symbolic determinants, and any sequence Fn of faces inside this Newton of Zn, the family determinant Fn Zn is called a Newton degeneration of determinant of Zn. And let Newton of VPS be the set of all Newton degenerations of the elements in VPS. Okay? Then what we have just shown is that it is in the closure of VPS because it lies in the orbit closure of the determinant. It can be shown to be in VNP also. It's not obvious, but it can be done. And now the conjecture is that conjecture is that Newton of VPS is not contained in VP, and this implies existence of bad exterior points. And as I said, it's supported by the complexity theory so far, the work of Edmonds, Kiao, Fournier, Maillard, in conjunction with this basic intuition complexity theory or belief that hard things kind of look random. Okay, it is also supported in a moment. I will say how, by the representation theory of quivers. In particular, the fundamental works of Drost, which is the tame-wild dichotomy, classification of these tame quivers, and some fundamental work of Schofield, Dirksen, and Wyman. And I'm going to talk about this on Friday. So Wyman, whose work plays a crucial role in this, all this, will first of all introduce to complexity theories what this quiver theory is, and after that I will explain its connection with this. But in brief, the point is this, that for any quiver Q without oriented cycles, which is just a graph without oriented cycles but multiple edges are allowed, one can associate, using the representation theory of quivers, a subclass of this VPS associated with that quiver. Okay, some complexity subclass, and this subclass conjecture, when this quiver is so-called wild and without oriented cycles, is conjectured is that so as it turns out, there is this tame-wild dichotomy. The quiver which corresponds to Edmonds theory, okay, is the simplest kind of tame quiver, and it is quite amazing because this tame means actually easy in representation theory, and wild means hard. And this tame classification that had come in representation theory long ago, this is the finite tame kind. So this finite type representation theory is the birth of representation theory. So the representation theory knew from its birth that this kind of algebras are actually the easiest thing. And in their definition of this easy thing, the word complexity occurs nowhere. I mean, they never use Turing machines, they never use complexity measures. And it's amazing that the birth of P actually occurred as the simplest tame quiver according to that theory, which according to them is easy, and according to complexity theory turned out to be easy. So this coincidence is quite remarkable. And in fact, the conjecture would be that whenever the quiver is tame, actually these Edmonds kind results will hold. So that would constitute a far-reaching generalization of the matching theory to all tame quivers. But when the quiver gets wild, the thing suddenly would get wild, and then it says that the things would go bad. So now let me give to complexity. Yeah.
Can you go?
Yeah.
Just, you're going to give us reasons why you believe this conjecture and so on. I'm just wondering, suppose it's true.
Yeah.
Does it mean that GCT is not the right approach for
No.
determinant versus determinant?
No, it doesn't say that, because what do you mean GCT? If this is true, okay?
Because it would be possible that permanent reduces to the closure, but not to the...
No, but that is what all the evidence so far says, that the lower bounds for exact computation and like for example.
Yeah, so far, but this is against what's happening so far, right? I mean, this
No, because the thesis of algebraic geometry, as I said, is that to understand this, you have to understand this. Okay, so I mean that is the century-old thesis that you can't understand a variety without understanding pathological thing about. So far everything is going fine, and the thesis would be, which can be defined, so the GCT thesis, that they would go fine all the way as long as you will get the polynomial bounds. Of course, it can be defined. For example, if somebody shows that, let us say that you have a lower bound for say n to the a, okay, yeah, for exact computation. So right now the lower bound is n square, okay. Let us say that you get a lower bound for n to the 100, and say this would say up to some scaling you should improve on the existing lower bound. But if someone were to improve on this lower bound to say n to the 100 without improving on the border lower bound, that would constitute that GCT approach would not work. I mean there is.
This is what the conjecture said, that if there are bad points in the closure of the determinant, like exponentially harder
Yeah.
than the determinant itself, then it's possible that permanent reduces to them, but not to determinant.
No, it doesn't say that. If, for example, someone could, so this is a thesis which can be falsified. So, for example, if someone were to prove a lower bound like this for the exact computation without saying anything about the thing, that would be an evidence against GCT. That is what you are saying, okay? So, I mean, this is a thesis which can be falsified. So, the n square lower bound, let us say somebody improves it to n to the 10 and says nothing about the border, that is an evidence that GCT is not going to work. But on the other hand, if the things go hand in hand, which is all the evidence and the principle of algebraic geometry suggests, then it means that actually it is a difficulty of the problem, not the. So far everything is going hand in hand, even in the restricted model. I mean, so of course, I mean for complexity theories who would want to, I mean, it's a thesis which can be falsified, and this is a way to falsify it. Okay, so if it can be falsified this way, then actually it means that the GCT approach is not the right one, as you said. Okay, if it can't be falsified, it means that actually it is the difficulty of the problem. Either way, I mean this is science. Okay, so it's a thesis which people can try to falsify. Yeah.
I have another question. You said the simplest quiver, somehow they must correspond now.
I'm going to go there.
Are you going to define what this is?
For the simplest quivers, okay? For the simplest quivers. So that is what I'm going to.
But you did not define what this
Not here, because this uses, so for representation theories, this comes from what is called Dirksen-Wyman semi-invariants with the quiver thing. So, but I'm just showing complexity theory's simplest examples, okay, where what that family is.
Just a quick remark. I mean, in analogy with matrix multiplication, there is evidence that this boundary and the limit.
Yeah. There is asymptotic.
Between rank and border rank goes away for matrix multiplication asymptotically. So there is evidence for this.
For one problem.
Right. So that's
No. But what I'm saying is that, I mean, there is evidence, and there is evidence for permanent. So all I'm saying is that the current evidence thinks that you can't ignore a border. But this is something that the field of complexity theory has to think about, that if the GCT approach is to be falsified, this is a way to do it. Okay, otherwise you have to go that. Okay, so let us take this. You wanted to see the examples. Okay, so let's say that VSPQ consists of the single family determinant of Xn, where Xn is n by n variable matrix. In this case, this is the tame quiver, which is just one arrow between 2 points, and this
that's
actually.
a finite quiver.
Yeah, this is a finite quiver.
Yeah. But
No, but the complexity theories may not know what.
but that's like really much different from tame.
Yeah, it is much easier than tame. Yes, I understand. But this corresponds to matching theory in complexity theory. This is bipartite matching theory. And this Edmonds theory, actually, this is finite type symmetric when you have just one arrow with this involution. Then this VSPQ consists of the single family determinant Xn, where Xn is a 2 by n variable skew symmetric matrix. And this quiver actually corresponds to Edmonds P theory, because if I take all the Newton deformations of this, I get all the Tutt polynomials associated with the with non-bipartite graphs and all the faces.
What is this notation?
It's just involution on the thing. Okay, so I mean this is what is called a symmetric quiver. Quivers with some involutions associated on that. Okay, I mean, we'll worry about that on Friday. Yes, so this actually corresponds to the tame quiver, okay, a symmetric quiver, and this is now the general conjecture would be that if you, so these are of course that there is a classification of all tame quiver. The conjecture would be that this Edmonds type theory works for all tame quivers, and that would constitute quite a far-reaching generalization of existing matching theory to all tame things. Okay, because this is the current matching theory, bipartite. This is non-bipartite matching theory. Is generalization to all tame quivers would constitute fundamental generalization of Edmonds matching theory to all things. That is expected. Okay, because representation theory itself says that this is tame. But once it gets wild, the representation theory says that suddenly things go out of hand. So this quiver is 3 arrows, that is 2 points. This stands for just this, okay? Now 2 arrows is tame, this is tame. This is tame, and this is wild. So this is like the difference between 2 sat and 3 sat, okay?
The notation I'm used to, that now I don't know what that notation is, because normally 3 arrows corresponds to, let me ask sort of maybe Yerji, because I thought 3 arrows is G21, which is
What?
No, it's 2 vertices and arrows going one way. Yeah.
So
what he
what's-
wrote is right.
what's G21 then?
What is G21?
Yeah, the Dickey diagram associated to the F on
No, I'm not talking about tame. This is wild. This is the simplest.
I thought that's 3 arrows.
No, of course.
Not related to that. I mean, you're just classifying triple the matrices.
Matrices, that's it.
Okay.
And that is a hard problem. That is,
No, I know. Yeah.
this is the first hard problem without oriented cycle. And suddenly, this is a wild thing. And so, representation theory says that this is where Edmonds theory would not extend, and this is where the shoot-up would occur. So here VSPQ consists of the families determinant Zn, where Zn is a d by d block matrix with d equal to polynomial, any fixed polynomial, and its ijth block is the symbolic sum, where you take 3 variable matrices, Z1, Z2, Z3, n by n variable matrices, and their generic linear combination. So for every entry ij, you introduce variables x1 ij, x2 ij, x3 ij. So if I take the generic linear combination of these matrices, put it in the ij d by d block matrix, and these xij's are variable, then of course the Newton of VSPQ is in the orbit closure, that we know, but conjecturally this family, its new deformations would not be in VP, because this is a wild thing, okay? So as long as you have a wild quiver without oriented cycles, the conjecture would be this would kind of give the specific families where the shoot-up would occur. Now once this shoot-up occurs, then so the point is, now you have the orbit closure of the determinant. So you start with determinant, you take its orbit, and now here the things are shooting up. Now once that shoot-up occurs, then obviously the complexity of that variety, considered as a variety, is going to go up. So now what we are going to do is define the problem of de-randomizing Noether's normalization lemma, which is basically a fundamental problem from algebraic geometry, which is going to measure how complex this variety is. Okay, so this lemma was proved by Hilbert. So it says, given any projective variety x in P of C to the k, okay, of dimension n, there exists a homogeneous linear map from C to the k to C to the m, where m is polynomial in n, that induces a regular well-defined map on x. What do I mean by regular well-defined map on x? Any point on x corresponds to a line through the origin in C to the k. It means that homogeneous linear map doesn't vanish on that line, okay? So if it is regular, then it is regular in the sense of algebraic geometry, and such a map is called normalizing map. Hilbert showed that any random psi has this property as long as m is greater than or equal to n plus 1, but deterministic construction of this psi, which is what we call is the problem NNL, is hard. Okay. So now if we use the standard representations of psi and x, that is, x you define it by giving its equations in this ambient space, polynomial equations, and psi you define by giving its actually the transformation matrix from C to the k to C to the m. Then in the case of our problem, x is going to be the orbit closure of the determinant, and this is going to have dimension exponential in the dimension of m. So in that case, the specification of psi itself requires exponential space in n. So there is nothing you can do. I mean, the output itself requires exponential space. So that is a bottleneck. So actually the problem is hard for trivial reasons. Okay. So But here now we are going to consider only the case when X is an explicit variety, such as determinant of Y. So I'm not going to define this notion of explicit variety today. Basically it means a variety that has a specification of bit length that is polynomial in its dimension. So in this case, we are going to specify this orbit closure by just giving a circuit for the determinant, okay? So that is a fundamental specification coming from complexity theory, which is very different from the standard specifications in algebraic geometry. Okay, only then do we actually get anything non-trivial of this problem. So this is tomorrow we'll see that the explicit varieties don't actually have to be orbit closures. I mean, it's a large class, but this is the one that we are going to focus on today. Then the problem NNL is, so let X be this orbit closure of the determinant embedded inside projective space V, where V is the space of polynomials in Y of degree m. Then given any matrix B, let psi of B from V to C denote the linear evaluation map that maps f of Y belonging to V to f of B. Okay, so you just evaluate it. So that is a linear map. Now given a set cal B, B1 to BL of m by m matrices, let psi B from V to CL denote this map which just evaluates all these maps at the tuple. So you just get the tuple of evaluations. Then a lemma, I mean it's a non-trivial fact from using algebraic geometry, that actually there exists a small set B of integer matrices of total bit size poly m, such that the psi B from V to CL induces a regular normalizing map on the orbit closure of the determinant. So such a small thing exists, and this follows from intersection theory in algebraic geometry. It's a non-trivial fact. Now this actually allows us to now define the problem NNL. So we are going to restrict ourselves to only such maps which have such succinct bit specification. So this map you don't have to specify given this matrix from V to CL, you can just specify it by giving these matrices, okay? Yeah.
But then it cannot be complete for X space.
No, it can't be complete for X.
Yeah, so when you started and drew this picture of the chasm, there was a potential gap between NNL being in X space and being in...
No, I'm not saying that it...
Once you restrict yourself, I just want to clarify this.
Yeah.
Too. Once you restrict yourself to explicit variety,
Yeah.
we already know that the problem is in BPP.
No. No, that's... No, random, that is the whole point. I'm going to say because of this thing, exponential shoot up, it's not in BPP, not because this is a construction problem. And to verify whether, so for example, okay, this is small, right? Yeah, this is an important point. Now you take a random thing of this size, actually it would be the case that it is with high probability normalizing map. But to de-randomize it, you have to know.
I'm not asking about de-randomization, I just said it's in BPP.
It's not a decision problem. It's a construction problem.
Sure. So okay.
It's a Monte Carlo algorithm. It has.
Will solve it.
Yeah, so it has a Monte Carlo. So it has a Monte Carlo poly M algorithm. That is what you mean. Okay, correct.
So for this kind of problems, there is no chasm.
No, there is.
For the de-randomization, but
No. For this kind of problems itself, there is a chasm. Because to remove that randomization is a very hard problem. I will explain in a moment. Because of this shoot up on the boundary. You can't remove this randomization, because if you want to cycle through all these things, okay, you have to verify whether that thing is actually a thing, and that verification itself takes X space. That is a problem, okay. So because of that, there is a chasm, even for this, because for determinant, it is this kind of problem only, okay. So that this is an important point. So I just
wanted to contrast it with the picture in the beginning. Now it's it's really a different chasm. We are talking about explicitly de-randomizing this Monte Carlo algorithm.
Yes, but the current deterministic algorithm for this is in X space.
Yeah, like many BPP problems.
Not BP, Monte Carlo.
But also for many BPP problems, the best deterministic algorithm we have is exponential.
But this is X space. I mean, it's much worse than X. That's what I'm saying. I mean, I will explain. It is not in X because you can't verify that this. So this is the whole point. That if I give you, okay, a matrix cal B. Okay, so I give you a cal B, B1 to BL. Okay, I want you, okay, verify, is this a normalizing map?
That's the best upper boundary.
Is in X space. That is the problem. Okay, that is why everything should, and that is in X space because of this shoot up on the boundary. So that chasm does refer to exactly this. Okay, that is the thing. Okay, so now the problem NNL is, given M specified in unary, construct a small set B such that psi B is a normalizing map on this orbit closure of the determinant. Okay, and now what is the current complexity? I am not talking about this. The current complexity is in X space. Okay, I mean, because given such a thing, the best that you can do at present is actually in X space using Grobner basis theory, and the result, the current techniques don't work because exactly this problem, that there is a shoot up on the thing. I mean, if there was no shoot up on the boundary, this problem would have been actually in P space, because what would you then do? You can then use all this coherence algorithm, for example. Okay, because once you know, so the thing is, let us say that there was no shoot up on the boundary. So you know that there is some control over the circuit size on the thing. So there is, say, m to the 100. Okay, you know that everything is m to the 100. Then you take this beta to be more than m to the 100, m to the 1000. Now you have to just verify that it is a correct thing for all the circuits of size m to the 100. Then now you can reduce it to Hilbert's Null-Stella and do it in P space. The point is that algorithm won't work because there is a shoot up in the circuit size. Okay, so that is the whole, and that is a very delicate problem. So because of that, it is in X space, not X. So that picture I drew is correct exactly for this. Okay, so now the space complexity is exponential because the dimension of the ambient space PV containing this is exponentially in M. And if we could prove that every point in this has a small circuit over C, then exactly it would have followed from the existing techniques, Heinz-Schnorr, Coirant, that NNL is in P space. But the main obstacle is that the existence of these bad exterior points on the orbit closure of the determinant, which is why getting it down from X space to even X, we don't know how to do it at this point. And now the result is that the stronger GCT1 conjecture implies that NNL for delta of det M is in quasi-det, that is can be reduced to, can be reduced to computation of determinant of 2 to the polylog M size matrices, which is in quasi P. And then we can ask, is there a converse to this result? Okay, so let us say that somebody tells you that the NNL for orbit closure of the determinant is in det or is in P. Can you get a lower bound for the permanent? You can't. For the permanent, you can't get any lower bound, but you can get a lower bound for the some exponential time computable multilinear polynomial in n variables. So in the opposite direction. So the equivalence theorem says that there exists an exponential time computable multilinear polynomial in n variables, which cannot be approximated infinitesimally closely by symbolic determinants of size O2 to the n to the epsilon, if and only if, ignoring a quasi prefix, the NNL for the orbit closure is in P. So if you could put it in P, you would get a lower bound not for the permanent, but you will get it for some exponential time computable multilinear polynomial. Now there is actually also a variant of this result for the so-called shallow circuits, which is important because the shallow circuits have been investigated quite a lot in the recent days, because there is this remarkable result that the arbitrary algebraic circuits of polynomial size can be reduced to depth 3 circuits of sub-exponential size. Okay, so using these depth reduction techniques for in the algebraic complexity theory, you can. So this result, in conjunction with that, implies the following result. It says if there exists an exponential time computable multilinear polynomial in n variables that cannot be approximated infinitesimally closely by depth 3 or depth 4 homogeneous circuits of size O2 to the n to the half plus epsilon for some epsilon greater than 0, then NNL for det is in quasi-det. So now here there is some interesting phenomenon which is worth noticing. So what there is some phase transition here. So here it says that if I could So if I look at this exponent, so if I get lower bound of the kind in this model at 2 to the n to the half plus epsilon, okay, here, then that would, what happened?
Probably touch your computer, maybe that will help. Well, it helps over there at least.
Can somebody tell?
It's okay. Continue.
Okay. So, if you have if you get lower bounds of the kind 2 to the n to the half plus epsilon, then you will get you will get that the NLL can be brought down to quasi-dead. There are already lower bounds, so 2 to the n to the half, these lower bounds already exist here, okay? And in fact, even the lower bounds of the kind 2 to the n to the half log n, I think exists, yeah? And the thing is, for the computation of the determinant, so this is where actually you can compute determinant, okay? Now, as I said, as I will see, into the half, into the half, yeah? So, at determinant can be computed at 2 to the n to the half, okay? If you can go past determinant n to the half epsilon, you will, the problem, the difficulty of NNL enters in. As long as you can't compute determinant, okay, and as long as you can't compute factorization of multivariate polynomials, that difficulty from algebraic geometry doesn't show up. So here we have something called this part, I mean the model you can call in analogy with this tame wild classification in represent. This is a tame model because here you can't compute the determinant, okay, and that is why the lower bound for permanent here is actually a statement about the weakness of the model. The moment you can compute determinant and multivariate factorization, moment you go here, in fact you can show that even if you go to the 2 to the omega into the half log n, you will get non-trivial implications for NNL. So there is a phase transition here at the exponent 2 to the n half log n. As soon as you compute determinant, the problem, the nature of the problem changes. So now, so that is the main result. So let me give the basic proof idea. Okay. So first, as you said, Avi said that you get a polynomial time Monte Carlo algorithm just from what I stated. Okay. So in the original work of Hilbert, it was not a polynomial time Monte Carlo algorithm. It was exponential time. It was exponential time because the size, the bit size of that set cal b was exponential in the original thing. But it can be reduced to polynomial using this work of fundamental work in algebraic complexity theory due to Heinz and Schnorr. Okay. So first you reduce the number of random bits from exponential to polynomial. That is the first step. Okay. Then now you want to de-randomize this algorithm. Okay. Now as I said, if you want to de-randomize it with the unconditionally, the best that you can do at this point is X space. Now you de-randomize this algorithm using this GCT1 conjecture. That is actually what is the key idea. That is what actually gives you the way to handle the things on the boundary. So if you do that, then you put that this is the fundamental hardness versus randomness principle in complexity theory. So the work of Nissan, Wigderson and Cabernet-Simpaglioso. So you use that in conjunction with that and the efficient factorization of multivariate polynomials. So this work of Kaltofen, this actually lies at the heart of this proof. So these three things together actually allow you to de-randomize this Monte Carlo algorithm conditionally, assuming this GCT1 conjecture.
To be a tutorial, maybe you could say a little bit more about what A and B are?
What is A?
Hardness versus randomness in efficient factorization of multivariate polynomials.
What is that? No, I mean they are separate tutorials. They are separate tutorials, I think.
I said
And they would be not this. Okay, yeah. I mean there are experts sitting here. All of them are sitting here. Well.
Right, there are also non-experts here.
Okay, you take it as a black box, and maybe it will become. At this point, you take it as a black box. Okay. Important thing is all this works only in the models in which the determinant and multivariate factorization can be computed efficiently, because this Kaltofen's work is crucial. The point is to deduce from a lower bound anything non-trivial about NNL. NNL is about solving polynomial equations. If you can't factorize polynomials and if you can't compute linear equations, you are not going to conclude anything about NNL, because after all it's a problem about solving polynomial equations. So all this only works in the models in which the determinant and multivariate factorization can be computed efficiently, not otherwise. Okay. So that is the basic proof idea. And now, so this is now the GCT chasm. So this NNL right now is currently in X space. As I said, the main reason for all the complications is it starts with the failure of dichotomy. This Newton VPS, as you have shown, the Newton deformation of any symbolic determinant is contained in the orbit closure of the determinant, and there the existing complexity theory indicates that the exponential size shoot up in the circuit complexity would occur. And representation theory gives some specific examples. Basically, these families associated with some wild quivers that are contained in the orbit closure of the determinant. And once you have these wild points in the orbit closure of the determinant and exponential shoot up, then currently all the evidence supports that this is not contained in VP or even its sub-exponential analog as conjectured. And once this is once you have the exponential size blow up on the orbits on the boundary, this is actually the most important part. Now all the work on de-randomization etc. in complexity theory suggests that if you want to construct a heating set against a class of circuits, that heating set you can't beat the size of the circuit. That the time to construct such a heating set would be polynomial in the size of the circuits that you are trying to hit. And so if that is the case, okay, so in that case, I mean, it would go against the basic principles that you can't hit against a class of circuits of exponential size in polynomial time, not even in sub-exponential time. So all this suggests that the NNL for delta of determinant A may not be in sub-x. If that is the case, then assuming GRH and robustness of valiant conjecture, all this happens. NP is in P/poly and polynomial hierarchy collapses to the second level. And with stronger bit things, it would follow that P is also not equal to BPP. So how are we going to deal with all this? So now in the GCT, the view we adopt is that all these conjectures, NP not contained in P/poly, that polynomial hierarchy does not collapse, that P equal to BPP. These are all, I mean, by now these are all profound conjectures of complexity theory. It doesn't really matter whether they are true or false, as long as they lead us to something profound, their job is done. Okay, I mean that is the way we are. So for example, if these conjectures lead us to the collapse of the hierarchy, well, I mean that would change complexity theory in a much more profound way than what if they were true. Okay, so the thing is, these conjectures are profound, and whether they are true or false doesn't really matter, as long as they lead us to something deep, and that. So the way the program has been designed is, okay, all the evidence now is going against, unless the GCT thesis is falsified, as said, and then so now just let us assume at this moment that they are true, okay, despite all the evidence to the contrary, and let us try to justify them. So the program would be, let us assume that for the sake of argument that they're true, try to justify them, and the program would be such that if actually they're false, the program itself would lead to falsification. So it doesn't matter, assume that they are true, try to get the justification, and if they are not true, the thing, I will explain that on Friday, it itself would give how to falsify the thing. And as long as something deep comes out, we are all fine. So before, for example, so right now, of course, for the orbit closure of the determinant, there is a problem. We don't even know it can be de-randomized or not. Let us ask the question whether NNL can be de-randomized for some intermediate explicit varieties. So as
I want to understand. So if we have generators or even set theoretic equations, explicit set theoretic equations for variety.
Yeah.
Then,
what do you mean by explicit? What do you mean by explicit? I mean, this is complexity theory. You can't use that term loosely.
okay, so I will tell you exactly.
What is it?
By explicit.
Yeah.
I have, say, so we're only dealing with varieties invariant under group action.
No, but
So
it is.
So it's ideal as a module for the group.
Yeah.
And I give you, so of course we have sequence, so I have to give you a sequence of representations for that group that occur in the polynomial ring that cut out the variety set theoretically.
No, how are you going to specify those equations?
Let's say there's some very, well, the module is very simple to describe, and then to get the equations from the module, you have to do a sequence of symmetrizations and skew symmetrizations.
No, for example, in GCT thing, like if Kronecker coefficient vanishes, okay, that module is easy to describe, correct? And from that you can get the equations of the variety. That would be considered explicit because, say for example, for some V lambda, okay, so for some partition lambda, so the rectangular
I give you a sequence of partitions that is enough. Okay? So,
lambdas.
a sequence of lambdas, yes.
And what is the bit length of lambda? Okay, that is why.
I don't understand that. Like, let's just say
Okay.
bit length of lambda. That's not.
That is the issue.
Let's just say the bit length of lambda is enough to, small enough to make you happy. Okay. Then is that a de-randomization of Noether normalization for that variety?
No, because just that is not enough.
So what additional do you need?
You need to compute those matrices, okay, that succinct matrices. That is not enough. That would only tell you that NNL is in the exponential hierarchy, assuming GRH, okay? Because once you have those explicit equations, you can run this coherence algorithm on the ambient space. But the dimension of the ambient space is exponential in M.
But my understanding is you just want to see if this linear space misses this variety, and if you have the equations for the variety explicitly.
But the point is you are using the phrase explicitly in a very optimistic, like a mathematician. I mean, what I...
There's nothing I can do about it.
Yeah, so the point is, we'll talk offline. I mean, you are not going to make me happy because I'm so we'll talk offline because that is going to give you an exponential hierarchy algorithm. It is not good enough for complexity theory. It is not. I mean, believe me, just equations is not going to give. We'll talk about. Okay. Yes. We have fortunately. Okay. Can NNL be de-randomized for intermediate explicit varieties? Okay, so for arbitrary explicit varieties, this is hard. And for intermediate, and we'll see that yes, and that itself would have some important implications and so-called Klein's Erlangen program, because Hilbert proved this Noether's normalization lemma in the context of Klein's program. So it does lead to some polynomial time algorithm which has some fundamental implications in that program, and we'll see this tomorrow. So you see that the GCT program, I mean, it doesn't really matter whether these conjectures are true or false. The GCT program has already delivered something on the lower bound front, as I said in the beginning of the program itself, and which is currently the only non-trivial implication of such a foundational conjecture in such a powerful model. And now it has delivered something on, we'll see that it has delivered something significant on the upper bound front. As long as it keeps on delivering, we'll just take the journey with that spirit. I mean, at the end, whether the conjectures are true or false, we don't know, but we'll just take the journey for the sake of journey without worrying about the end, and see what happens and leave the rest to time. So I think I will stop here. Thank you very much.
Questions or comments?
What definition of
Write down the definition again, so I was kind of confused about it.
Newton deformation, Newton degeneration? This?
Yeah, so it's
So I don't know why this is happening now. Yeah. Is it clear?
Symbolic matrix, the size is much larger than the number of variables. So you're plugging in linear.
So what I mean is the following. You take any matrix Z, okay? Yeah? So you take Z1 to Zn some variables. Now each entry you either choose it to be any Zi, okay? Or any complex number. like in Valiant's projection thing. That's it. And take its determinant, expand it as expand it out, okay? Take the exponents, take its Newton polytope. Take any phase of that Newton polytope. Just restrict that to phase. That is Newton degeneration. Yeah?
Since you're on this page, can I ask a question? So are there any interesting questions for, say, n equals 3, 4 on this page that would like inform the theory at all? Or do we always
On which page?
about Newton degenerations, interesting points in the boundary of the orbital determinant that are so if I pick a face of my favorite determinant, 4 by 4.
Yeah, I think this is again the complexity theory is always we think asymptotically, 4 by 4 we never think about, and mathematicians think of 4. So I don't know, I mean this is...
But if there was something surprising in the boundary for the 4 by 4 determinant, that would be very strong evidence for what you're saying.
So,
Even for 4
so
by
for example, you take, so I would say that you take this quiver, okay? Yeah? So I have given you the, even in the 3 by 3 case, okay, so there are three variables, and you take any n to d. I mean, I think you have to go to at least 12 by 12 or something like that, okay? Now try to see the Newton degeneration for that. But I don't know, you won't see asymptotics so easily, I mean, at 12, etc. I mean, you want to see that exponential blow, I mean, maybe you can run it, I mean, but you know the orbit closure of the determinant, the calculations go up to what? Peter?
There is something naive to do with, I mean, you have this polytope assigned to the determinant, and now you take this Newton degeneration, and the question is now, what can we understand about this polynomial? Maybe one thing one could do is look at the symmetries, whether because the determinant have lots of symmetries, and how about this?
So for example, no, I think the thing to analyze would be this wild quiver. This wild quiver, you know, try to understand the facial thing, try to, I mean, this is where the things would start going wrong.
I think the question was whether one can do something non-asymptotic, whether it's possible to understand it.
Okay, I mean,
Maybe look at the symmetries, whether one could destroy most of the symmetries to it then. Just as an indication that it could become more difficult.
I guess maybe
This can be
let me
done, I
rephrase
think
my
this can be
question.
analyzed mathematically.
As somebody relatively new, I'm looking for an entry point, and maybe I'm not ready to think about the full asymptotic problem. It's too difficult for me. So then I would just want to think about one particular problem that might be interesting and I could actually do something with.
yeah, so I think this wild quiver would be interesting to analyze and see the facial structure of this wild quiver and try to restrict to faces and so forth. So, you know, I mean, this is where the Edmonds kind of matching theory would not work. I mean, because this is the simplest wild quiver.
Can you elaborate on this and explain what this question would do with respect to this wild quiver?
So I have given the exactly. So for example, I have given the exactly. Yes, I have given this. Okay, so this is the VSPQ, right? So you take d by d block matrix, then d equal to some polynomial. I mean, I'm a complexity theory, so polynomial n. Okay, so you can take whatever. Yeah. Then ijth block is the symbolic sum. Okay, z1 etc. So I mean, just like there you have the Pfaffian thing, you have this thing. You take the Newton polytope, and now try to understand the facial structure. I mean, this is going to be much more complicated than that of the Newton polytope. Okay, so try to understand as much as you can. I don't know. I mean, is that a non-asymptotic?
Well, the other thing is if you do something for size 4 determinant, you may be able to generalize it to size n instantly, and then you're going to get some interesting polynomials. I mean, they may manifest itself very early.
I doubt it. I mean, 4 by 4 determinant is very, like we have done in permanent versus determinant, you hardly see anything.
I just don't understand this definition on point 3. I don't understand it well. I think there are 3 arrows. What do you want to, and then what do you do exactly? I mean, you assign to it a certain determinant.
You have triples of linear maps.
Yes, and these are the Z1, Z2, Z3, or what?
So we took in a reference for the definition of the VPSQ for a general Hilbert Q with the for the title.
Huh?
So these are examples.
Yeah.
The reference
But I don't
Oh, so the reference is, so the reference for general quivers is, general quivers. I think I have given the reference. Yeah, this Schofield, Dirks and Weiler. Okay. That is for general field. So how to associate such things?
Any other questions?
Yeah.
We are not supposed to ask general questions. We're not supposed to ask it this on Friday. But what sort of surprised me is that all of a sudden you assume the GRH. Well,
What is it?
you
GRH.
assume the GRH. What does number theory have to do with it?
I think this is this result by Pascal Poirot that you can put
Yeah.
Hilbert's Nullstellensatz into the polynomial.
I mean, you're surprised that GRH is coming in, or?
Polynomial equations has a complex solution. Oh, no, you can, this is in P-space anyway, but you can,
But you can put it in. Why do you use GRH?
that's the question.
That was my question.
Yeah, you're right. Because
My number theory.
Why do you need GRH? Because GRH enters in your result between you have forgotten what you I will explain to you what.
maybe you can explain.
Okay.
I might have a related question because you also assumed robustness of Valiant's conjecture.
Yeah.
What evidence do you have to? Why do you? Because it seems to lean very strongly on that. Because you can only conclude.
That is exactly what he was saying. So basically, if Valiant's conjecture is not robust, basically it would mean that GCT program it would falsify GCT program. Okay. So basically, this is the thing.
There is a GRH there is a 10P in P/poly, which
What?
we don't believe.
Which is what?
There are three statements there, that's what he's asking. You have the robustness of Valiant's conjecture, the fact that NP is not in P/poly. But it seems the most fragile thing in PSM, right? The GRH.
GRH seems the most fragile.
The GRH, NP is not in P/poly, and the robustness of Valiant's conjecture. One has to give.
Which one? What is your pick?
My opinion is the robustness of Valiant's conjecture.
No, my thing is that. See, my thing is that for robustness of Valiant's conjecture, we have physical evidence.
Just everything we did is consistent with it. That's
Yeah,
not
but for
physical.
P/poly, have you ever seen a non-uniform circuit?
Yeah. I've seen only
No. See, the point is non-uniform. I mean, this is exactly the point that was made by Gordon. When Hilbert gave this non-uniform circuit, that this is mythology. So this is modern day mythology. Okay, because we have no experience with non-uniform circuits. We have experience, like with GRH, we see the zeros lining up. I mean, this is a statement about this physical world about which you can carry experiments. Okay, with Valiant's thing, I mean, there are lower bounds which say something. This P/poly is our imagination.
So you believe that NP is in P/poly?
If something has to give in, that has to give in. Because other things, there is physical evidence. For this is our imagination. So if something has to fail, our imagination would fail. The reason for that is the following. Okay, let me give you why I think.
But just let me make sure that it's consistent with something else you believe. So there could be a non-uniform reduction from permanent to determinant.
Non?
A polynomial size non-uniform reduction from permanent to determinant. This will be the same as NP in P/poly.
Yeah. So this non-uniformity is a problem because, for example, we have the experience of IP equal to P space. We don't know what is non-deterministic. We don't know what is co-non-deterministic. There, non-deterministic, that was our imagination. Randomization is our experience. One imaginary thing started alternating with something we knew, and you know what happened. Now here, when polynomial time hierarchy, two imaginary things are alternating. I mean, when at least there we knew one thing and it was collapsing, what makes us so sure that we know what is going to happen? When
I agree, we don't know. I'm just checking consistency. So NP in P/poly, you are willing to believe, but wait just a second. But algebraic NP, VNP, being in VP, non-uniform, you don't believe.
algebraic what?
That permanent is reducible, non-uniform.
The non-uniform version, or the algebraic non-uniform version.
No, I mean, what is the difference between VP and VNP problem and what you are saying?
Yeah, so it seems you believe that permanent does not have polynomial projection to the term.
No.
Even non-uniform.
Yes. What I'm saying is that this non-uniformity, if I have to give in something, I will give up on non-uniformity because this is the world I live in, and here I see I have an evidence, and we have the experience of IP versus P space. I mean, you know that we're making our guesses about the world that we didn't know about, and we know what happened. Okay, so about this imaginary world, I mean, I don't know anything, so I'm not going to take any guesses. Okay, and so among these three things, at least I have some physical evidence. For physical evidence, this, as far as I'm concerned, is our imaginary world. Okay, so something has to give in. I will give up on the imagination.
Okay, so let's thank Ketan again. And we'll meet again at 10:50.